So he's a director of the research at CNRS, the Institut de Physique at Nice. So he has his research interest is like vast, basically. So I guess if you want to summarize in few words, is transport in complex systems, cloud microphysics, planet formation, microseminar navigation, and basically stochastic structures in turbulence. And today he is, I guess, going to talk about stochastic structures in turbulence.
Thank you.
Okay, so
thank you, Sanjeev.
Yeah.
Thanks for the invitation. So it's okay. I understood that I'm not talking in front of an audience of people who are very specialized in turbulence. So there is some pedagogical background, of course. So what I want to tell you about is connect to the real butterfly effect, which is the thing known from Lorentz, and which now has been reassessed somehow in more modern terms, in terms of a spontaneous stochasticity. And I will try to tell you why this is important in order to understand the nature of turbulent flow. So the thing I'm going to talk about is based on work with Alexei Mailibayev, who is at IMPA in Rio de Janeiro in Brazil, Simon Talabar, who is also at Infini, a colleague, and Nicolas Valade, who is finishing his PhD on a part of the thing I will show you. So to start with, so certainly this you know it. So what is now commonly attributed to Lorentz as being the butterfly effect is actually the exponential growth of perturbation. Okay, so you think about you have some kind of dynamical system. You linearize the difference between two trajectories. You get a linear system which is driven by the gradient of your right-hand side, etc. And then what you get is an exponential growth at long time. And if you make this non-autonomous, you have results on ergodicity, etc. So which allows you to define the Lyapunov exponent. And so what this means, it means in particular that if you control the initial error that you're doing and make it to 0, you're able to have the discrepancy between the two systems equal to 0. Okay, so this is what it means. It means that it's a linear dependence on the initial perturbation. And actually, Lorentz, he didn't introduce himself to the butterfly effect. So actually, just for the short story, so he was talking more about a seagull in the bay, in the Hudson Bay in New York City, who was able to do a storm or a cyclone in the other hemisphere. And he was asked at some point to give a seminar on that in a conference, an invited seminar. And he was asked to send an abstract and title, and he didn't do it. And so the person who was inviting him, organizer of the conference, decided that there was this idea of something flying, giving this thing, and he coined the name butterfly effect. So actually, it's not Lorentz himself. So what Lorentz in his famous 1969 paper was claiming is that there are two kinds of behavior that one can expect in a system. Something where the error can be made arbitrarily small by reducing the initial discrepancy. So this is what we call this deterministic chaos. Okay? And the other thing is that in other cases, two replica of the system reach diverging state, no matter how small they differ initially. And he associated this kind of, so this is the real butterfly effect. And he has associated this idea to a system which has an infinite number of degrees of freedom and which is able to have enough energy at small scales. Okay, so this was the main idea. So the thing is that now so it has been rethought a bit. So mainly thanks to the work of Palmer, who is a geophysicist, in order to really understand how this is affecting, for instance, predictability of climate, of meteorology, etc. Because you really need to be able to estimate something more than just a Lyapunov exponent. And the thing I want to discuss a bit is to try to address the question whether or not this is actually an intrinsic feature of turbulent flow. If turbulent flow are always having this kind of extreme unpredictability. So I will give you a short example. Inspired by turbulence, I will come back to this thing. So it's called the Peano problem. So imagine that I have an ODE like that. So I have time derivative of some separation, and this is supposed to mimic some velocity difference. And imagine that this velocity difference, this velocity field is Roth. So that at r equal to 0, I have something which is non-Lipschitz. Okay, so I have some power of r which is less than 1. So now you know that unicity theorems requires the right-hand side of your dynamical system to be Lipschitz. So you are breaking that. So it's continuous, but not Lipschitz. So which means that solutions, because it's continuous solutions exist, but as it's not Lipschitz, they are not unique. So now the thing is that, imagine that you take a regularization. So in my case, I have two ways to regularize. One which is to smooth out my singularity at r equal to 0 by adding some cutoff, eta. And the other one, which is to add noise, because noise has a regularization effect. Okay. And so now, imagine that I consider this equation, which is just a regularization of the above equation, in the limit when I take both this regularization and the noise to 0. Okay. The result is the following, is that so now, this is an example, because it depends how you make things go to 0. But in case when you don't put any small scale regularization, so which means that you make eta going to 0 first and keep some finite noise, noise is enough to regularize. So basically, in order for a stochastic equation to have uniqueness pathwise, so of all trajectory for a given noise, you just need the drift to be continuous, to be continuous. Okay, so that's enough. So it's continuous. And so now, in this regularization by noise, what you can show is that actually you have, so you imagine that you start from 0, so you put initial condition at 0, which is my singular point. Then I look at different realization. So initially, when I'm close to r equal to 0, the drift doesn't count, just noise, so you have diffusion here. And after some time, you have two branches which are created. One which grows like a power law of time with positive values, and another one with negative values. So of course, I mean, because of this strange power, you have this super diffusive long time behavior. Okay, where the variance of your unknown is growing like t to some power 2 alpha with alpha related to h. But now, if you think in terms of probability distribution of the probability flow of transition probabilities, so what is shown here is the difference. So I rescale it a bit differently. So now again I take all my trajectories, but I divide by the root mean square value of my displacement of r, and what I see as a function of time is that initially, so I have a blurry distribution, and when time is increasing, I have two branches which are appearing, which corresponds to these two branch in the solutions. And if you want, the gray color here is representative of the probability distribution. And what you can show for this simple example is that, and for this specific case, is that the limiting flow is not deterministic. So if now you look at solutions, how the probability distribution of these solutions is going when you make regularization to 0. So the transition probability to go from 0 at time 0 to RT is a sum of two delta. So you have two masses, which correspond to the two branches. So which means that it's not deterministic in the sense that you don't have a unique solution, but you have a probability measure over solutions. And this is somehow the idea which is behind spontaneous stochasticity. Okay? That's, if you want, even if I make the noise to 0, I keep some finite probability in some finite effect of the noise in my solution. Okay? So that's why it's spontaneously stochastic. So now I will come to turbulent flows. So how does this relate to turbulent flow? So I guess that this sounds something to you. So yes, please. Yes.
So in this one, so you're taking the first eta to 0.
Yes, exactly.
And eta to 0 without noise.
So if you don't put any
New going to zero first.
yeah, exactly. I mean, your solution is staying at 0.
Staying at 0, but like if I just start with the initial equation which is 0 plus,
Yes.
then like the first equation.
Yes. Exactly. So there are different ways to think about the limits.
Okay.
So you can also modify the initial data in order not to start from 0.
Okay.
And then you will have at any time later a trace of the initial distribution. So imagine that you put.
Does it go to this two, like 0 plus
Exactly,
0 minus
exactly.
0?
So imagine that you put, I don't know, 1/4 at negative values, 3/4 at positive values. It will change the mass here.
Yeah.
And somehow this is some kind of degenerate example, which is easy to understand. But the thing is that here there is nothing universal. So the distribution that you get depends on the protocol you follow. Okay. Yes. Yeah, exactly. You can. Yes, exactly. And this is how you can prove that. Yes, exactly. Yes. So now coming to turbulence. So I guess that you're able to know that these three aspects are characterizing what we call turbulent flow. So the first thing is the fact that energy transfers and mixing are enhanced by turbulence. The fact that it's random and unpredictable. This is or unpredictable and possibly described by something random also. And the fact that it's multi-scale, that you have many scales which are activated, and intermittent. Intermittence in the sense that you have anomalous scaling in all these cases. And then so somehow the graal of people doing research in turbulence is to try to understand links between these different aspects. Okay, so this is a very broad view. But I will come back to this three bubble diagram. So what is fluid turbulence? I'm considering incompressible fluid turbulence. So I'm starting from the incompressible Navier-Stokes. So this is very basic. I guess that most of you know that. So I'm starting from the incompressible Navier-Stokes equation. So which means that incompressible, if you want, I prescribe density to be constant. So which means that if I look at the mass conservation, it's giving me that the flow has to be divergence free. Okay, so that's the continuity equation is giving you divergence free. And now if you look at the evolution of momentum, basically what you do is that you consider a small fluid element, you apply Newton law to this small fluid element, it's the sum of the forces, and this fluid element is also moving with the flow, so which means that this second order, and of course the time derivative of the position is the velocity field, so which means that the second order time derivative of that is taking this form, in the sense that, so you have time derivative of the velocity plus the material derivative following the flow. And this is what makes the flow nonlinear, because it's creating interactions between different scales. And then on the right-hand side, I mean, it's pretty simple. So the thing is that since you want to impose divergence free, and that this term is not conserving that divergence, basically you remove the gradient part of this term. So divergence free means that you are purely solenoidal. So if you put some acceleration, in some acceleration, some gradients, you have to remove it. So it's just that. And if you want, pressure is another unknown in your equation, but at the end it's like a Lagrange multiplier, or if you want, it's a projection of this operator. And then the next thing that you have is dissipation. So you have molecular friction between the fluid elements, and this is modeled as a diffusive zone. And of course, you have to maintain some state, some turbulent developed states, and you add some external forcing to this thing. So this is the forced incompressible Navier-Stokes equation. So now the thing is that usually, so if you balance these different terms, you can measure the importance of this advection compared to dissipation. Okay, and this is how you define what is called the Reynolds number, which is just the ratio between this dissipation time and advection time. So which means that when Reynolds is very large, dissipation is long, so it has no effect. And typically when Reynolds is large, because dissipation has no effect, the flow cannot maintain some steady state, and is becoming unstable and chaotic. Okay, so this is Navier-Stokes equation. So now turbulence in a nutshell. So now what do we mean by a turbulent flow? Is that now if you do a global kinetic energy budget, so imagine that I take my position on the three-dimensional periodic domain. So I'm writing a global energy budget of my from Navier-Stokes, and what you get is that the time derivative of the mean energy has to be balanced by two terms, one which is the viscous dissipation, and the other one which is the injection. So all the terms which are due to advection, or the pressure term, I mean, they don't contribute to this energy budget. And so now the idea is the following, is that so you're injecting energy at large scale, the flow is unstable, it's creating smaller scales, smaller eddies, and it's transferring energy to smaller scales, and so on, until it's reaching sufficiently small scale so that you can get big gradients and you dissipate. Okay. So this is the idea of Richardson cascade, so which is more than 100 years old, and associated to that, so you can. So there is a phenomenology which is due to Komarov in the 40s, which is the following thing: is that so if you have a statistical steady state, so you need the dissipation to balance the injection. So now assume that you compute some kind of energy content at a given scale L, that I will write UL squared. So the thing is that if you are at large scale, when dissipative terms are not important, somehow in Navier-Stokes equation you have to balance this time derivative with this advection. And what it means that the typical, so you are balancing these two, means that the typical time scale of evolution at the scale L is equal to U square, I mean, is satisfying this thing, so it's just the turnover time. So it's the scale divided by velocity. Okay, so it's not very different from dimensional analysis. And now the next thing is to say that the energy which is contained at the scale L is increased with a rate which is given by this motion of the eddies, and dissipated at a rate which is this nu by L square, which is just the dimensional, the scaling of the viscous term. And so if this thing is larger than that, it's when the Reynolds number, which is now scale dependent, is larger than 1. Okay, and so as long as this Reynolds is larger than 1, so you are in this kind of cascade scenario, and what you get is that the energy transfer, the increase of energy at this rate, if you want, which is U squared by tau, has to be exactly the rate at which you inject energy. Okay, so you have this tau L minus 1 U squared to be of the order of epsilon. So that at the end, the typical velocity at the scale L is scaling like L to the 1/3. Yes, please. Yes.
Something that's externally determined.
Exactly. Yes.
So you can decide whatever, it doesn't matter.
It doesn't matter.
The point is that there is always going to be the transfer will always be in this direction.
Exactly. Yes.
And I'm not sure I fully understand why. I mean, what the, so that's why my question is completely naive. But from what you said, why is it that the transfer has to always be downwards to the smaller scales?
So what you would like is also energy to accumulate
Yeah.
upscales.
Then
So it's the case in 2 dimensions.
it's not that this analysis is not
Yes,
giving you.
yes. But I will come. It's connected to something different, which is I will come to that, and it's some indirect evidence that this is the case, and it's due to the fact that even if you make this large-scale Reynolds number in 3D, so I mean 3D, large-scale Reynolds number going to infinity, you always have a finite rate of energy dissipation. It's something which is called the dissipative anomaly, which is true for energy in 3D, and it's not true for energy in 2D. But I will come to that. So now this is what's happening. So when Reynolds, the local Reynolds number is much bigger than 1, but when this guy is 1 or smaller, then this happens at small scales, and this is introducing a new scale, which is called the Kolmogorov scale, eta, which is obtained by using the proper powers of the viscosity and the kinetic energy injection rate in order to obtain a scale. And it's exactly the place where this Reynolds L is equal to 1, assuming that velocity is scaling this way. Okay. So this is the thing that is more or less the main ideas of Kolmogorov's phenomenology, is that inertial range dynamics depends solely on the transfer rate, on epsilon, which is the velocity at which you transfer kinetic energy in the inertial range, and the scale L at which you observe the thing. And then from this hypothesis, you can derive many dimensional predictions about what's happening in the turbulent flow. So now the question that you want to address is how much one can get from information on the inertial range, on this viscosity-independent dynamics, by looking at solutions of the Navier-Stokes, neglecting the viscosity. Because it will be much easier to be able to neglect the viscosity in order to get some ideas about how things are scaling, how things are dynamical, etc. And so concretely, I mean, if you do some kind of scale-by-scale energy budget, so this is a small Reynolds number, but I mean, it doesn't change when you increase the Reynolds number. So the inertial range is somewhere in there, you see. And what you see is that you have the different contribution to the scale-by-scale energy budget, which are such that viscous diffusion doesn't do anything, and the nonlinear transfer, so the transfer scale-by-scale of kinetic energy, and the forcing are exactly compensating to give the right number. So here it's normalized in such a way that it's minus 4 epsilon. Okay, so that's the idea, is that indeed when you look at scale-by-scale energy budget, there is absolutely no contribution of the viscous term. And now the thing is that since you are maybe able to neglect this viscous term, the question is, if I don't have this term, I have extra symmetries in my equations. And in particular, for instance, I can use also a variational principle in order to construct my solutions, which is something where I have to minimize the Lagrangian flow, so the position of fluid elements at time t as a function of their initial position, in such a way that they just minimize the kinetic energy. So here I'm not writing the contribution from forcing, but there is a variational principle. There are symmetries, there are Noether invariants, and all these things is we don't know how to apply them to describe the inertial range dynamics. In particular, you have many symmetries which are preserved. I mean, which are preserved by the dynamics in the absence of viscosity. So of course, I mean, time and space translation and Galilean invariance. So Galilean invariance is when you move with a constant velocity. These things are also preserved by Navier-Stokes. But then you have two other symmetries, like time reversibility, because if you kill this term, you can flip the arrow of time, t minus t, u minus u. And the other thing is that because of the absence of this term, you also have scale invariance. So you can rescale time, space, and velocity as you want with an arbitrary exponent h, and the equation here isn't changed. Yes?
So this one, what are you talking? It's like keeping one term at a time.
Exactly. So it's if you want, it's as if I was taking a Fourier transform of that. Okay. And multiply by the case mode.
For example, this blue one is keeping only the left two terms.
Exactly. The blue one is just for a fixed scale, is measuring how much this thing will correspond to, will act on the global So it's as if I was coarse graining on the scale L, and write the energy budget at this scale of the coarse graining, okay? And then I look at, so this term and pressure are contributing if I do this coarse graining. It's only when I do the full average that they don't contribute. And here what I show is how these things are varying as a function of my coarse graining scale.
So if I have to do it, like let's say, so I'll neglect all the time on the right side and do it or no? So like if I have to get this curve.
Yes.
And numerically, how will I get it from that equation?
So usually you do it with Fourier transform.
Fourier transform, but
Yes.
keeping all the terms.
Keeping all of the terms.
All the
Exactly.
And then
And doing a balance in Fourier space
and then
of kinetic energy.
I identify this, let's say yellow one is.
The yellow one is exactly obtained by the forcing at a given scale times the velocity. I mean, it's the power of forcing. So it's the contribution to the local budget. Okay. So the first thing that is known, so this is this dissipative anomaly, is that time reversibility is broken. So in the inertial range, and if you make Reynolds to infinity, you don't recover the Euler equation with a time reversible behavior. And in particular, what is known from many different numerical experiments or actual experiments is that the limit of the viscous dissipation when Reynolds is going to infinity, so if you want, when viscosity is going to 0, is finite. Okay, so if the flow is able to create, if you decrease viscosity, the flow is able to create smaller and smaller structures such that the singular nature of these structures is exactly compensating the fact that you take viscosity to 0. Okay, so if you want, the gradient square of is growing like 1 over nu.
You can't get back the non-list, purely non-list to the thing that you need.
No, exactly. So you have to think differently.
Singular limit, if you like.
Exactly. Yes.
U going to 0 limit
Is a singular limit, and you cannot just apply the different symmetries, which is so this is what is.
You say that it's scale-dependent phenomena, that if you have the viscosity is smaller than a certain scale,
Yes.
that on larger scales it looks like
Exactly.
viscosity-free fluid.
Exactly. So the thing which is telling you there is that what's happening here at very small scale, close to the place where I dissipate, is actually affecting the whole picture, and the fact that here you get this specific shape for the scale-dependent energy budget.
You can't really sort of block it out.
Exactly. You cannot do anything at small scale that will reproduce the same statistics. And so I mean, basically these are, you see, but you have to go to rather large Reynolds number, but at the same time, so what you see is that at the end the dissipation is almost independent of Reynolds, but also, I mean, so I don't know if you're familiar with Reynolds number. This 10 to the 3 is a teacup. Teacup is 10 to the 3 Reynolds. So which means that when you start so clouds will be 10 to the 7. Okay. So basically, you are clearly in all natural flows, you are in this regime of a very large Reynolds number. And this is typically a slice of a turbulent flow developed, so maybe a point somewhere here. And so what you see is that, so it's a slice, so it's a 3D, and this is the instantaneous dissipation field. And what you see is that this guy is organizing on large scales. So you have places which are more white and places which are more black. This is a log scale, so which means that more white means that maybe you have 1,000 more dissipation than in black areas. And when you zoom at a very small scale, you see, so the smallest scale, commercial scale, is somewhere small like that, smaller than these filaments that you observe. And it's because of these very strong filaments that you keep a constant dissipation. So this is the hand waving picture. So now, yes, different systems, different way to force, boundaries, no boundaries. But it's mainly numerical. Sure. Yes, please. And so the way you do it, no, the viscosity is entailed in the Reynolds number. So the Reynolds number, if you want, is just a way, it's just like the inverse viscosity, but rescaled by your typical velocity and typical length. Okay, so for a given forcing, this large scale velocity and large scale size are fixed. So for instance, if you have a pipe flow, you will choose for you will choose the speed that you put at the beginning of your pipe, and L you will put the diameter of your pipe. See, so yes, so this is the thing, is that we don't need to have viscosity going to zero. It's Reynolds to infinity. But it's easier to think about viscosity going to zero because it's more ugly to write the equation, the Navier-Stokes equation, in a non-dimensional form with a Reynolds number, etc. So it's just like so it's called the inviscid limit. Yes. Yes, sure. Yes, exactly. Yes. So now, second thing. So now the thing is that, so again, Kolmogorov. So there is one exact relation in turbulence. So all this cascade picture was just a phenomenological picture, which is called the Forfy flow. So of course you need to assume that your flow is a homogeneous, isotropic, stationary, etc. And what you get is that the third order moment of the velocity difference between 2 points. So I look at the velocity increment, I project it on the separation, and I take the third order moment. So it's negative. So the first thing is that it's negatively skewed, so it's tilted. So the skewness is negative, and it's proportional to L. And this is a strong result. I mean, it's just like delta U cube is proportional to L. And you remember that what the phenomenological ideas was giving is that UL will be proportional to L 1/3. So it's consistent with that. Except that this is true only for the third order. Okay. And why the third order? Because if you want, I mean, to do it short, if you think about Navier-Stokes equation, if you make an energy budget, you multiply by U. Okay, and here what you get is something like a gradient of U cube. Okay, and this gradient of U cube has to compensate in a steady state, has to compensate the input of the force if you can neglect viscosity. Okay, and this is typically how this so this is minus this third order moment as a function of scale, compensated by what you expect. The line is 4/5, so it's log scale, which makes things flatter, of course. But you see that asymptotically, you seem to converge to this 4/5, but it's very slow. Very slow and very hard, because it's, if you want, the distribution is almost symmetric. It's slightly tilted, so which means that at the statistical level, it's very hard to calculate exactly this small skewness. So now there was, so you see 41, now I'm moving to 49, slowly. So there was a conjecture by Onsager, so he worked also on turbulence at that time, and which was connected to this idea of a finite dissipation in the limit of this dissipative anomaly. And his conjecture was to say that in order to get a finite dissipation, you need the Lipschitz exponent, the Hölder exponent of, you need your flow to be non-Lipschitz, and the Hölder exponent has to be less than 1/3. Okay, so it was a conjecture based more or less on ideas connected to that, and it took some years to prove it. So at the end, it was finally proved in these papers by Buckmaster and Isett quite recently, that indeed, in order to, for a dissipative weak solution to the Euler equation, has to have a Hölder exponent less than 1/3. Okay. And 1/3 is exactly the critical point. Okay, so yes. Exactly. So it's this delta LU is the increment. The increment of velocity is going like separation to some power less than 1/3. Okay. So what are the conclusions? Is that of course turbulent velocity fields are Roth. I mean, in the limit of viscosity going to 0. So you have this idea that you need to get this Rothness. Okay. And the thing is that from that you can think about constructing dissipative weak solutions to the Euler equation. So now you go to the Euler equation, you neglect viscosity, you say, okay, I will understand this equation in a weak sense, in the sense of measures, if you want. And the thing is that then they need to, in order to dissipate, they need at least to have this Hölder exponent less than 1/3. And so this was the idea of some work in the from 2008 to still now people are doing this kind of thing. So they were able, using some techniques from PDEs, which are a bit so it's convex integration, so it's something which is a bit complicated, to have a constructive way to do solutions, to obtain solutions which of the Euler equations which are dissipative. Okay, so even if you have no viscosity, they are able to dissipate because of this Rothness. And the thing is that the other surprising results that these mathematicians obtained is that in these constructions, almost all non-smooth initial data, so you take initial data which has the right exponent, they are non-unique. I mean, they lead to non-unique weak solutions. So they can prove that the set of initial data with a given Rothness leading to non-unique solutions is dense in L2, so in the space of solution with finite energy. So which is super strong, which means that you will never see a unique weak solutions to the Euler equation. Okay. Yes. Yes. Exactly. You take nu equal to 0. You take nu equal to 0. Exactly. So if you want to make it short, is that now you have to interpret. So forget about the viscous term. You have to interpret the Euler equation in a weak sense. So you have to multiply by test functions. And the thing is that you cannot. So usually what you do is that you are able so if the solution is smooth, you are able to change the derivative from one side to the other. Here, if you have singularities in your solution, somehow when you try to do this kind of integration by part, you have contribution from singularities, which are giving an additional term, and in particular from this nonlinear term. Okay, so this is to make it short. Yes, 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 exactly. No, you get a contribution from singularities, because somehow. So, for instance, you have to you see when you I will show a case which is Burger's equation for which it's clear. It's very clear because you have shocks, you have discontinuities. Yes. Exactly. Yes. Yes. So now, so this is the thing. So no, hard to find uniqueness. Second thing, which is known now since again Kolmogorov and Obuchov 60s. Is that the field is not safe-similar. So we were talking about this exponent 1/3, but actually, if you do measurements, what you can, so for instance, if you look at the moments of this velocity increment to the power p, they scale with a non-trivial power which depends on p, and these are typically the different measurements. The way the power depends on p is universal. So see what I show you is data from a wind tunnel, and some data in a von Karman flow, which is two counter-rotating helix, and the thing is that the value of the exponents are universal. There is no doubt about that. They don't depend on the details of the way you excite your flow at large scales. And so this also you can think in these terms, is that now if you look at the PDFs of these velocity increments at different scales, and you look at the different curves. So you go from something which is, so it's a log and not log here, okay? So which means that something which looks like a parabola is a Gaussian. So at very large scale, which is this curve, is Gaussian, almost Gaussian. And when you go down scale, you start to create heavy tails, like that. Heavy tails in your distribution. Okay, so which are close to log normal or stretch exponential. Hard to know. So this thing means that in addition to this spontaneous breakdown of the time reversibility, here you have also breakdown of scale invariance. Scale invariance, which is satisfied by your inviscid dynamics, is broken by turbulence. So now, next thing, which is the thing. So I'm coming back to the first example of this Peano differential equation, and telling you is that now that you know that the flow is Roth in order to dissipate, the thing is that now if you take fluid particles, so you just look at characteristics of your flow, tracers, so solutions to the ODE where things are just moving with the velocity field, and you pick some initial data. So you have, this is the Lagrangian flow, and now you do as usual. So you try to see the separation between two of these guys. So there is something which is known again since the 20s, almost for 100 years, 1920s, not the 2020s. So which is Richardson diffusion, is that at sufficiently long time, the separation between these two guys will be super diffusive. So R square will go like T cube, with again a constant in front of it, which is universal, with no, and you're losing dependence on the initial separation, as in the case I was showing before. Okay, so it's a kind of explosive. It looks like diffusion. If diffusion for two realization of your noise, you can start from the same position and just go away with a separation which is independent of the fact that you are at zero or at a different distance. Here it's the same, except that we are in a turbulent flow. And this materializes this way, so you can start things very close to each other. And after a time, so a time after which this is valid, you have this explosive, instantaneously explosive separation between the tracers, and then everything is going in all directions. And this is not due to the large scales. It's really at the inertial range of your flow. So you can also measure it this way. So this is results from numerical simulation. So you measure this mean square displacement conditioned on the initial separation. So different initial separation. So initially, you start from your value, so at t equal to 0. And you have a first regime, which is this curve thing, which is ballistic, where things are just separating ballistically. And then at very long time, all the curves are collapsing to a unique curve. Okay, so it's, people will say that it's not enough to show this graph. Okay, and so this is leading to the last thing, which is the fact that your flow is also breaking down, in the sense that you cannot give a notion of transport of fluid elements, because somehow the map, which is giving you one position at time, the position at time t of something initially, is ill-defined because of that. Okay, and it connects to these ideas of spontaneous stochasticity, as I was telling you, but it's from a Lagrangian viewpoint, so following the fluid elements. Yes.
Super ballistic, right?
It's a super diffusive, yes. Yeah, it's super ballistic if you want, because ballistic will be t square. Yes.
T-square.
It's faster than ballistic.
Yes, so but then what makes it faster than ballistic? Because I thought if there is velocity, you cannot go more than the...
Yes, but the thing is the following, is that, remember my first example where I had dr dt goes like r to the h.
Yeah, I understand.
So it's, in this case, we have h like 1/3.
But if I think of it...
So let me show you the first this one. Oops. So this is exactly the thing that we have. And so now you see the R square is going like 2 alpha. So just put H 1/3.
Yeah,
So you get 3 halves here, and 3 halves times 2 is giving T cube. So it's just
suppose if I think of like some tracer.
Yes.
Here, so you're saying that it's something pushing more than the. So you need more.
Yeah, exactly. So the thing is that ballistic means that you keep the same velocity difference at all time. Here, when you move to a larger scale, the velocity is also increasing. Exactly, that's what it means. Yes, like R to the 1/3. But you see, the thing is that if it was R, it will be exponential. It will increase exponentially. So, okay. Next point. Yes, please. Yes. The flow in the sense of the Lagrangian flow is the flow map, if you want. The flow map, this map here, the thing which is mapping position at time t as a function of the initial position. Because if you want, in the limit, when you make separation to 0 and Reynolds infinite, what you will get is that any two trajectories will just spread like that, even if they start from the same initial position. So which means that you don't have a unique image. Okay, you start from things which are the same position, and they give possibly different. And the last, yes. Yeah, it's a kind of blow up, but it's not localized, so it's everywhere. And the last thing that I wanted to talk in this picture of turbulent flow, yes.
For that to happen, at least some noise should be involved. I mean, if you start with identical positions.
Yes. 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 You have some noise, but even if you make the noise to 0, you still have this thing. And this is something that I will again explain here.
It's not intuitive.
It's not intuitive. Yes, it's exactly this idea of spontaneous stochasticity. But here let me take this example. So this example is two-dimensional, okay? And it's Kelvin-Helmholtz instability, so I guess that most of you know it. So I have a flow which has a discontinuity. The upper part is going to the left, the down part is going to the right. Okay? And now and this is something which is always unstable. So you put any kind of perturbation, the growth rate of the perturbation is proportional to the wave number of your perturbation. So you put k, you have a growth rate like k. Okay, so so which means that in principle, you put k equal to 0, you have an infinite growth rate. K equal to infinity, you have an infinite growth rate. And that's the point. Yeah, so if you want, is that any small perturbation will allow you to grow super quickly.
It has to be some infinitesimal.
Exactly. So the thing that we have considered here is to put, as an initial perturbation, we put a small noise. Okay? And of course, in order to do a computer simulation, we need also a viscosity. Actually, we use different kind of regularizations, also point vortices, etc. And the thing is that you see so this is the typical picture that you get. So you have some noise initially. This noise is amplified by the instability, and it's creating things where the scale is increasing with time. And now we did the following experiment, is to say, now we take both the noise and the viscosity to 0. Okay? So for instance, this is one kind of experiment. So we choose the noise to have the same amplitude as the viscosity. And we take different decreasing values, so from dark to light blue, of the viscosity. And this is typically the picture. So we look at the separation, so the the mean square difference between two solutions with different noise. And so what we see here is, so let me start from the largest velocity, viscosity. So we first have a regime. So this is more or less the epsilon. So initially I have something where the discrepancy is epsilon. Then it's increasing exponentially. And then I go to the saturation regime of my instability. Okay, and it's following this line. And now if I decrease viscosity, and at the same time the amplitude of my perturbation, I go down here, and I'm also increasing my growth rate, because the growth rate is controlled by the smallest wave number I have. Okay, because I told you all growth rate are proportional to k. So to the largest wave number, I'm sorry. And so now the thing is that it's growing faster exponentially, and it's saturating to the same curve. So you see, it's this idea that if you were to take the limit viscosity to 0, you will directly fit to this curve. So which means that all solutions, even if you had made them no noise, as soon as you have put viscosity to 0 and noise to 0 in the proper way, basically they will spontaneously separate and create this kind of organization at large case. Okay, so this is really this idea of spontaneous stochasticity. It's exactly the idea of what is known by what Lorentz had in his mind when he was talking about the butterfly effect. No, not the butterfly, the seagull effect. So now I'm back to my triptych with my 3 balls, and so this is more or less like a to-do list. Okay, so I'm not claiming that I have any clues on what's happening exactly. So you remember I had this thing that enhance mixing and transfer. So I connect it somehow to the dissipative anomaly. So the fact that even if you take viscosity to 0, you get some finite dissipation of kinetic energy, and this connects to the breakdown of time reversibility. And this was the enhanced transfer. Now there is this idea also in predictability that you have Eulerian or Lagrangian spontaneous stochasticity, so that the flow, the velocity field or the flow itself could be ill-defined. The flow, the Lagrangian flow or the velocity field could be ill-defined. And I connect it to some breakdowns of descriptions of turbulence in terms of flows. And the last thing, which is this multi-scale ideas, is that things are intermittent in the sense that you have anomalous scaling, you don't have scale invariance. And this is another thing which is broken from this idea of being able to describe by Euler equation. So then I have tried to link this different thing. So in between dissipative anomaly and Lagrangian Eulerian spontaneous stochasticity, the thing which is clear is that the mathematicians have been able to show that if, in order to get a weak solution which is dissipating, you get non-uniqueness of the solutions. So maybe it means that you cannot interpret solutions as a unique field. You have to think in terms of probability distribution over fields. The second thing is that between dissipative anomaly and intermittency, of course, the main question is what about all this distribution of singularities that we have? And this is something that people have been working on it for years, and there is no clear link between this scaling of the velocity and the fact that you have a dissipation. So the thing is that there are some phenomenological link which are made in between them, but there is no real result saying, I can connect intermittency to dissipative anomaly. And the link that are existing dates back from Komarov in 1962, and it's called refined self-similarity. So they can link the two in some way. Measurements show that things are fine, but it's very difficult to understand why. And then, in between intermittency and this Eulerian spontaneous stochasticity, so the thing that actually we observed for this very specific example of Kelvin-Helmholtz flow is that the way we were getting, the kind of statistics that we were getting in the limit was independent of the kind of noise we were putting or of the kind of regularization at small scale that we are putting. So we tried different regularizations, different kind of noise, and statistically we were getting the same thing. So which means that maybe this spontaneous stochasticity is able to trigger some universal properties of the flow, some universal statistics, which will connect to the fact that, for instance, we observe scaling exponents which are universal. So maybe the link between these two is this selection of universal statistics. And I will stop there. Please. What? Yes? Yes. If there is no viscosity. Exactly, yes. Even if you have no viscosity. Just by taking the limit of viscosity going to 0.
But it's true, right? Even there is no dissipation. You apply a magnetic field, the time reversal symmetry always breaks.
Yeah, of course. You have other ways to break the symmetries.
Yeah.
But the thing is that the fact that you're considering limit of infinite Reynolds number or viscosity to 0 is selecting in a very specific way the solution in such a way that all solutions are dissipating, even if they solve the inviscid equation.
Thanks.
Yes, yes. Yes. Intermittency, it's complicated because in 2D you have two cascades. So in 2D actually you have two quadratic invariants. So in 3D you have only one, which is the kinetic energy. In 2D you have two. You have
the inverse of the.
You have the energy and also the entropy, which is the mean of the vorticity, the mean of the square vorticity. And the thing is that depending which cascade you look at, the things are different. So for instance, the entropy cascade is smooth. Okay, so you have some, so you don't have scale invariance, but it's smooth at the same time. So you see, it's very different, and because it's smooth, you have you don't expect any dissipative anomaly for the entropy, and conversely, the inverse cascade of energy, so energy is cascading upscale. So there you expect to be able to by having some mechanism to remove energy at large scales to show that in some limit you get the right thing. But in this inverse cascade, you don't see much of intermittency, which is, and 2D is a bit non-universal also, degenerate.
Maybe I'm not understanding exactly, but the fact that you have initial data which is not smooth, there is always a question of scale, right? At which something is not smooth.
Exactly.
So, or you can average it out, and we expect any physical system to be fundamentally not smooth, right?
Yes, sure.
So but here one is saying is that if you have that whatever this holder, whatever the level of that's the regularity.
Yes.
That you will you be shielded at some larger scale from this non-uniqueness is the kind of the question. You said something about the fact that you'd get, you'd have to look at probability distributions for solutions, not unique solutions, but over, thinking about it. But would you at a larger scale where you can sort of assume smoothness and so on, be able to recover some kind of uniqueness in that process? Or, I'm just thinking in terms of, the breaking down of scale invariance and everything.
Here the situation is different. Uniqueness is at small scale, if you want. Uniqueness to make things smooth, you need the viscosity, and the viscosity is damping everything at very small scales. Okay, so you have a smooth field at small scales, And typically, you see the scale at which it's becoming smooth has nothing to do with molecular scale. I mean, so for instance, in the ocean, it's 1 centimeter.
Yeah.
So below 1 centimeter, everything is
It's
smooth.
on mesoscale.
Yes, but it's really a scale where the hydro description is fine. And the thing is that here it's more like it's the small scales are smoothing, but if you were to blur the small scale, you will not be able to know exactly what is your solution. This is,
Okay.
and it will be extremely sensitive to this noise.
Yeah, okay.
Okay, so that's why it's relevant to meteorology. Because in meteorology, I mean, they don't resolve smooth scales at all. So they cut things in places where it's clearly non-smooth, I mean, irregular. And the thing is that they quantify very poorly the error that they are doing and the sensitivity to this thing. So Lawrence was a meteorologist, so his aim was really to be able to quantify this way the meteorological models.
So actually in chaos theory, I mean, the number of degrees of freedom for the system should be at least 3 to exhibit chaos, right?
Yes.
So in this constraint, so is there the dimensionality constraint is given imposed, or it has to be only infinite degrees of freedom all the time? So
no, I think that's the you have to get infinite. So in order to get spontaneous stochasticity,
you have to
have infinite number of degrees of freedom.
Okay.
But you see, if you take some you don't need a continuity.
Okay.
You see, infinite is enough, and there are some systems which are like shell models.
Okay.
So some model of turbulence where you write a discrete equation, which are displaying this spontaneous stochastic behavior.
Okay.
Okay, so but in the limit where you put noise at large
Okay. So
shell, I mean at small scales, and you make also the cutoff going to infinity. So you need an infinite. Somehow, Lawrence, what he had in mind was that it's true for systems which are having enough energy at small scales, which have a finite amount of energy at small scales.
Can you construct some entropy-like quantities which you can show that? Like, can you construct some entropy-like quantities like P log P, some over P of U, I guess, right? And then you can show that it's an increasing function of time to show that the breakdown of
which what
I
P log P, but over. So for instance, if I take
I guess P of U, I guess, right? Or
yes, this is something we didn't do. But for instance, here. So for this, because you see, this is this I can do different ensembles. So this is one case of the separation energy between two solutions. But I could make many different realizations and construct a probability of seeing this stuff at a given time. Where my source of randomness is the noise that I put initially. So this is what you mean, that I could try to quantify the dispersion of
some kind of like this H theorem, right? I guess, but I don't know what is the quantity. Maybe like P of the velocity field.
Yeah, but in the space of velocity field.
In the space of velocity field, I guess, like I mean the same way you would do for the phase space density, right?
Yes.
I mean that's one measure of time irreversibility, I guess, right?
Yes.
I don't know.
I don't know, because it's a field, so it's complicated. It's complicated and it's not one point.
Yeah, it's not.
So you cannot just play with the probability of.
Yeah.
But the best way the best evidence for irreversibility is this thing, is the fact that velocity increments, when projected on the separation, they are skewed. So which means that time reversibility, you will make U minus U, and what you expect for a time reversible system is this to be 0. So I mean, this is a proof of irreversibility somehow.
There's no more question. Let's thank Jeremie for
Thank
a
you.
very nice talk. And also, yeah.
Oh, thanks.
Something. So, Mr. Mararai,
Good.
it's a bag for you to carry it.
Thank you. Thanks. Thank you very much. Very nice bag.